My name is Star Sullivan. I'm the superintendent of the Wastewater Division for the City of Missoula. I put together this PowerPoint presentation to give everybody an idea of just what we've been doing out there for the last 2 years, explain some highlights to the project, why we did the project, and what the results of that project have been. We did it for three principal reasons. One was to achieve water quality improvements in the Clark Fork by reducing phosphorus and nitrogen discharges as required by the Voluntary Nutrient Reduction Program agreement that the city signed with other shareholders in the watershed, the Clark Fork watershed. The Clark Fork River was identified as being impaired by algae, and excessive algae growth is directly related to phosphorus and nitrogen discharges into the river. So we wanted to get those under control. To increase, the second reason was to increase wastewater treatment capacity for future growth in Missoula. The third reason was to eliminate chemical disinfection, namely chlorine additions to the plant effluent by using ultraviolet light disinfection. So this removes any chemical additions before the water goes into the Clark Fork. The project highlights: we added secondary treatment system to biological nutrient removal. Chlorine disinfection was eliminated and replaced with ultraviolet disinfection, and the liquid treatment expansion to meet the growing service area. The result of this project is to comply with the VNRP requirements, the voluntary nutrient reduction requirements, to reduce phosphorus and nitrogen, and to increase capacity to 12 million gallons a day on a yearly average basis. To give you a little background of where Missoula's been at with its wastewater treatment is the early 1900s, the original sewer system just dumped raw sewage into the Clark Fork River. Subsequent to that, up until the 60s, it was just on-site cesspools or raw discharges to the Clark Fork River. The wastewater treatment for centralized treatment in Missoula is in 1963. They built the first centralized treatment plant. It was just a primary treatment plant. In 1974, in compliance with the Clean Water Act, the Federal Clean Water Act, we added secondary treatment to improve treatment to bring it up to higher standards. Throughout the 80s and 90s, we did several improvements, projects, and capacity, which brought us up to about 9 million gallons a day. In the year 2000, we began the design of the advanced secondary treatment, which we just completed. And in 2004, as I've said, we have just completed that. This is an aerial photo of the original treatment plant. You can see it's pretty small there, right there. This is the Clark Fork River, and then the city of Missoula out there. Many people have been here their whole lives know that Reserve Street did not go clear across the river back in those days. 1974, we did the secondary upgrade. This section of the plant here was the primary treatment, and of course we've added the secondary treatment here as well. Throughout the 80s, 90s, we expanded out headworks. I'll explain a little bit more what that is later. Improved solids handling and expanded out the secondary treatment. This is the facility just prior to our most recent project. As you can see here, here's the treatment plant. And over here is eco-compost. This is where we take all of the biosolids removed from the treatment process back to beneficial reuse. This aerial photo was taken last fall, pretty much midpoint of the project. As you can see here, this is the existing plant here, which we did several modifications and upgrades to. But we've added here the advanced secondary treatment, the BNR, the biological nutrient removal treatment. The biological nutrient removal and capacity upgrade, it was funded by a $5 million EPA STAG grant, reserves and SRF loan paid for by customer fees. We're what's considered an enterprise fund. All of our operation And capital expenditures come from people who pay their sewer fees. The total project cost was $18 million. The design was completed by Morrison Merrily Inc. Of Helena, in association with Stantec Consulting, who is in Vancouver, BC. Stantec was our process engineers. They're one of the premier companies for biological nutrient removal. And then Rockingham Design did the architectural work. Construction was a company out of Utah. It was Ames Construction, in association with Mountain States Electrical and several other local contractors. This is a schematic of the plant. As you can see, it's fairly complex, and I'll try to explain this through some following slides exactly how this works. But this is really just to give everybody an idea of just how complex the process is. This is a very simplified process. As you can see, it goes through the headworks preliminary treatment to the primary clarification. Thirdly, to the advanced secondary treatment. Fourthly, to disinfection. That's the fluid train or the hydraulic train that we use before discharging into the Clark Fork River. But there's a second flow-through train, which is all the solids removed from the process. And as I said earlier, all those solids end up at eco-compost for beneficial reuse. To recap, the headworks preliminary treatment, that is to remove solids to the landfill. That's kind of all the debris, the sticks, the garbage, sand, gravel, things like that. A headworks preliminary treatment, large non-biodegradable objects, rocks, sticks, sand removed to protect downstream equipment. Results, we get about 7 dumpsters and debris hauled to the landfill each week. We have BFI. I just pick up those dumpsters. Primary clarification. What happens there is basically it's a physical process. We remove the settable organic and inorganic matter is settled out of the solids. Floatable fats, oils, and greases are also removed at that point. The result is the liquid will go on to receive further treatment and remove solids receive further treatment as well. Advanced secondary treatment. What happens here is organic matter is used by the microorganisms as food. The ammonia is converted to nitrogen gas and released into the air. Phosphorus is removed from the water and accumulated by the microorganisms. The microorganisms take up those phosphorus, which ultimately end up at eco-compost, which enhances those biosolids for beneficial reuse. The result of this process is we've stabilized the water. It has low organic matter, low nitrogen, low phosphorus. Microorganisms and inert solids receive further treatment. Disinfection. What happens here is pathogenic organisms, those that can cause disease, are rendered inactive by the ultraviolet light. The result is a clear, stabilized water with reduced nutrient concentrations and low pathogen counts as it is discharged to the Clark Fork River. Solids digestion. What happens is we concentrate the organic matter and microorganisms which are converted to water and gas, methane and carbon dioxide specifically, which reduces the solids volumes by about half. The result is stabilized solids delivered to eco-compost for beneficial reuse, and the methane gas is burned in a boiler for the plant heating and energy needs. And to recap those processes from your home, headworks, primary clarification, advanced secondary treatment, disinfection, and the solids train is to the anaerobic digestions, where it's converted to gas and water vapor, and then the remaining solids end up at eco-compost for further treatment. I'd like to take you through some construction photos. Like I say, we were in construction for 2 years. I think it's important to note that all the time that we went through this construction, the 2 years, There was never one day or 1 hour that we could shut down the process of the plant. We didn't get any variance from any regulatory agencies, so we had to keep the existing plant meeting our permit limits and keep it operating at all times. This is the primary effluent lift station, a new building that was put in. You can see there was quite a bit of excavation and piping going on. Again, this is part of that primary effluent lift station, the new building here. Again, lots of excavating. A piping and equipment tunnel. We like to run these larger pipes inside of tunnels or galleries, if you will. If there's any problems, we can get in and repair these pipes rather easily. We did this wherever it was possible, physically and economically to do that. But you can see the floor here where they begin to build those structures. Again, concrete walls, concrete floors. Eventually there'll be piping that goes through these galleries or tunnels. As you can see here, the piping begins to go in. This is the primary effluent pumping station. The pipes that come up out of the ground, this pumps, it's an intermediate pump station within the plant to get it from one process to the next. This pumping station actually takes it from the primary treatment to the advanced secondary treatment. In addition to this project, one thing we decided to add to it was a new effluent outfall to the river. The original outfall dated back to the 60s, and we felt this would be a good opportunity to put a new line in. There was some cold weather work, as you can see. This is the ultraviolet disinfection system that we put in. We installed this in the existing chlorine contact basins. It's really quite large basins where you inject the chlorine at the beginning and the chlorine does its disinfection before it goes out. So there's quite a bit of time involved in that. This device here is actually a concrete pumping truck. More piping, more excavation, some fairly large pipes there. Again, the tunnels, the piping. This is the UV disinfection as it's going in. These racks right here, there are UV bulbs in here. They resemble very much fluorescent bulbs that you see in office buildings and different places. They're just a little bit different intensity, but as the water flows through these, it becomes disinfected by ultraviolet. And you can see the bulbs here. There's, I believe, 12 banks of these with 8 bulbs in each bank, 6 to 8 bulbs. The control mechanism for the UV system. This is the plant outfall. This is after the disinfection. This is where it's discharged to the river. This is an overhead hoist crane to pull those UV bulb racks out. Again, more excavation, more piping. Lots of pipes that are already existing in the ground. This is one of the difficult parts of the job, is that building on an existing site, you had to be careful not to break any of the pipes as you put in new ones. A new pipe going in here, and obviously these are older pipes that had to be avoided. The beginning of the new advanced secondary treatment, there were large square basins or tanks. As you can see, there was quite a bit of excavating going on here to take it below grade. This is one of the new secondary clarifiers that settle out those solids from the bioreactors. Again, excavation, lots and lots of concrete. The floor of the secondary clarifiers, lots of steel and concrete. In the spring, we had some groundwater problems, so we were, as we were pouring these floors, you can see this is groundwater that came up nearly to the top of the floor, so there was some difficult periods in the spring as the runoff began and we began to get high groundwater levels. Again, more reinforcing steel and concrete. The secondary clarifier tanks begin to take shape. The concrete's poured, the tanks are poured, and then they begin to put in the mechanical devices in the middle of the tanks to one step closer to full operation. As you can see in these pictures, this is a secondary clarifier, a new secondary clarifier that was put in. And these are these pipe galleries. They've got a large pipe in here, but you can see that these concrete walls and all of these tunnels are below grade. Again, one of the pipe galleries as they're putting more and more piping in. More pipes, big pipes. This is one of the existing circular clarifiers or settling tanks. You can see the bioreactor back here beginning to take shape. Again, more reinforcing steel, more concrete. The piping gallery and the bioreactor walls begin to go up. In these bioreactors, the microorganisms require quite a bit of oxygen. We have some aeration blowers, but to supply that oxygen to the microorganisms, we have these fine bubble diffusers, and it works not unlike a typical household aquarium, but air is bubbled up through each one of these heads to provide that oxygen for those microorganisms so that they can remove that phosphorus and nitrogen. Again, another picture is that are installed. We run water into these to test for leaks. An interesting thing happened when they were testing these. We tested them at one point during the winter time, and as these aeration heads, those fine bubble diffusers, blew air up through the water and then ultimately the ice, what they did is create these interesting stalagmites growing up out of the tank. But each one of these represents one of those fine bubble diffuse heads. As it blew up through, it created these stalagmites. Again, more construction photos. Secondary clarifier begins to take shape. More cold weather work. This is the bioreactor. We started this up, the new bioreactor. We started this up in February of 2004. And as you can see, it's a large tank of microorganisms and solids, but we're blowing air up through these, so that gives it kind of that mottled look. A finished new secondary clarifier. This is work beginning to convert the old secondary system into a biological nutrient system, nutrient removal system. This was a little bit more difficult work because working with existing structures and equipment and things like that took a lot of work. New walls being poured into the existing bioreactors, all new piping. Again, more excavation, more piping. These are we use the same exact air diffusers in the bottom of the modified existing tanks to get that air to those microorganisms. These are additionally with this air, which provides oxygen to the microorganisms as well as keeping them mixed. We have these propeller pumps which provide additional mixing, and then a slightly different type of pump that kind of recirculates those solids to keep them mixed together, to keep them in contact with each other so they can do their job. These are the aeration blowers that provide the air to those microorganisms. These are the blowers themselves. This is the discharge piping. and those feed all those fine bubble diffusers. The solids processing system improvements. One of the things is we normally use anaerobic digestion to stabilize those solids. We took one of our anaerobic digesters and converted it to a fermenter. What this fermenter does is create a food source for those specialized bugs, those phosphorus and nitrogen removal bugs. So it's a ready carbon source that kind of supercharges them. A new bridge. We completely revamped our digester gas system so we can more efficiently use that in our boilers. And we save a considerable amount of money by using that methane gas instead of natural gas for heating purposes. Again, work on top of the fermenter conversion. Excess gas that we produce off those digesters is flared off in a what we call a waste gas burner. This is the old existing one, and it was replaced by this new one. One of the problems with the fermenter is that it does have a lot of odors associated with it. And this square box here is something called the biofilter, which the air from that fermenter or any discharges from that fermenter ran through that to control odors. We put in an additional solids holding tank before dewatering. All the solids in the digester are either held in these tanks or digesters, go to this building where they're dewatered. We have a dewatering process, and then those semi-dry solids are sent to eco-compost for further processing and beneficial reuse. Some more pictures of those tanks. The associated equipment, the pumps, piping to move those solids. One of the things we did additionally with the project is we added a control room. One of the things we added with this project was a supervisory control and data acquisition system. It's a computerized system to control and operate the plant. More work on the administration building. Almost complete. Final site working and landscaping. One of the things that we chose to do on this project was to use zero-scape landscaping so that wouldn't be a lot of money or resources wasted on just mowing large turf areas. So Rockingham Design did our work out here, and I got to say that it's really a wonderful job. Sidewalks, curbing, and some more sidewalks. This picture shows the asphalt going in. I want to tell you that the staff was mighty happy to see this going in. Coming to work in a mud hole every day for 2 years was not fun. As you can see, there is some turfed areas. We've decided to keep them small, but the landscaping is beginning to look like something. Again, this is that zero-scape landscaping. It came out very well. And we did put some small turf areas in. Construction statistics. There was over 55,000 cubic yards of dirt and material moved to put these tanks in this excavation. 8,300 cubic yards of concrete. 1.2 million pounds of reinforcing bar. I think from some of those photos you can get an idea of that. And nearly 3.5 miles of pipe installed with this project. 160,000 person hours of labor. This is approximately 40 people employed over the duration of nearly 2-year project. Process startup and performance. UV disinfection facilities in operation by May of 2003. The advanced secondary treatment system started up in February 2004. The existing treatment plant system converted and placed in service in August of 2004. Final completion is October 2004. There's still some touch-up items. We still have some painters and some people out there just doing some final touches. To give you an idea of some of the results of this project, it shows you some historical phosphorus discharges into the river. 2001 pounds per day, 173 pounds per day. 2002, 195 pounds per day. 2003, 190 pounds per day. And in 2004, after we began the the new process, it dropped by almost 60%. Nitrogen as well. We saw a dramatic decrease after the plant came online, and nitrogen has been reduced by over 60%. And as we bring this plant online and we begin to operate it and adjust it, we should probably get even better results. One of the concerns with the plant in the past has been ammonia. And as you can see, the new plant going on process, we've virtually eliminated all ammonia in our discharge to the Clark Fork River. One of the measurements of sewage that we've always had to maintain was carbonaceous biochemical oxygen demand. And even that was reduced by about 40%. Total suspended solids, that's another measurement of sewage strength, was also reduced by over 40% with the new process. UV disinfection, we brought our bacteria counts down to very, very low levels. As you can see, historically, we've had some numbers in the thousands. 2003 was the first year we brought it on. There was some break-in periods of the new equipment, but as you can see, for this season, this disinfection year, those numbers are very low. Chlorine usage, of course, we've gone from 3,000 to 4,000 pounds annually of chlorine in our to disinfect our effluent, and of course in 2003 we eliminated that. As you can see here, we also test above and below the wastewater treatment outfall in the Clark Fork River. And as you can see, in 2004, we have really brought our ammonia concentrations very low, almost matching those that exist in the river before it even gets to the treatment plant. Soluble phosphorus has also come down. So what does the future hold? The city has adequate capacity to accept additional flow for a number of years. The city will continue to study additional treatment improvements, including a poplar tree demonstration project in 2005 to reduce discharge to the river. This is a new type of land application project where poplar trees are grown for various reasons using wastewater treatment plant effluents. It's going on quite a bit in Oregon and Washington. And then we're going to optimize the biological nutrient removal to remove even more nutrients from discharge to the river as we get more familiar and kind of adjust this plant in. The city will also implement a new solids treatment improvements in 2005 that will increase process and staffing efficiency. The city will complete a comprehensive treatment facility plan to update and ensure environmental and treatment efficiency improvements for the next 20 years. Well, I hope this was informative for everybody. If you have any questions, we do have an open house Tuesday, October 19th. It begins at noon. We'll be doing tours. We've got some audio-visual things that we'll be explaining more about this wastewater process, what we've done, where we're going. But we certainly invite the public to come out and take a look and see what we've done out there. I appreciate your time.